The 7 Cloud-Native Patterns, your blueprint for modern architecture. A cloud-native revolution beyond buzzwords to battle-tested patterns. Cloud-native architecture isn't just about running containers in the cloud. It's about fundamentally reimagining how we build, deploy, and scale software systems. These 7 patterns represent the distilled wisdom of organizations that have successfully navigated the transition from traditional monolithic architectures to cloud-native ecosystems. Each pattern solves specific challenges while contributing to a cohesive approach to modern software architecture. Pattern 1. Microservices Architecture, the Decomposition Foundation. The challenge: monolithic applications become increasingly difficult to develop, test, deploy, and scale as they grow. Team coordination becomes complex, technology choices become locked in, and small changes require full system deployments. The solution: the microservices architecture pattern breaks large applications into small, independently deployable services that communicate over well-defined APIs. Each service owns its data, can be developed by small teams, and can scale independently based on demand. The diagram shows the classic microservices setup with client applications connecting through an API gateway to multiple services, each with its own database. This pattern enables independent development, technology diversity, resilient failure, and granular scaling. Implementation reality: microservices introduce distributed system complexity. You need to master service discovery, inter-service communication, data consistency, monitoring, and deployment coordination. The pattern works best for organizations with mature DevOps practices and multiple development teams. Pattern 2. Database Sharding, the Horizontal Scaling Architecture. The challenge: traditional relational databases hit scaling limits as data volume and traffic increase. Vertical scaling, bigger machines, becomes expensive and eventually impossible. The solution: database sharding distributes data across multiple database instances based on a sharding key. The architecture shows horizontal scaling where data is partitioned across multiple database shards, enabling linear scalability. This pattern addresses throughput limitations, distributed load across multiple database instances, storage constraints, splitting large datasets across multiple storage systems, and geographic distribution, placing data closer to users for reduced latency and fault isolation. Implementation considerations: sharding introduces complexity in cross-shard queries, rebalancing, and maintaining referential integrity. Applications must be designed to work with partitioned data, and operational complexity increases significantly. Pattern 3. Event-driven architecture, the asynchronous backbone. The challenge: tight coupling between services creates fragile systems where changes ripple through multiple components. Synchronous communication creates performance bottlenecks and single points of failure. The solution: event-driven architecture decouples services through asynchronous message passing. Services publish events when state changes occur, and other services subscribe to relevant events. The diagram shows event brokers facilitating this communication pattern. This pattern enables loose coupling. Services don't need to know about their consumers. Scalability: asynchronous processing can handle traffic spikes through buffering. Resilience: systems can continue operating even when some services are unavailable. And extensibility: new services can subscribe to existing events without changing publishers. Operational complexity: event-driven systems require sophisticated monitoring, event schema management, and handling of eventual consistency. Debugging distributed event flows can be challenging. Pattern 4. Sidecar Pattern, the Service Mesh Foundation. The challenge: cross-cutting concerns like logging, monitoring, security, and service discovery create code duplication across services. These concerns are orthogonal to business logic, but essential for production systems. The solution: the sidecar pattern deploys helper containers alongside main application containers to handle infrastructure concerns. The diagram shows sidecar proxies managing communication, security, and observability without modifying application code. Key benefits include separation of concerns. Business logic stays focused while infrastructure concerns are handled separately. Language agnostic: sidecars work with any programming language. Consistent policies: security, retry, and monitoring policies applied uniformly. And simplified applications: developers focus on business logic rather than infrastructure. Service mesh evolution: modern service meshes like Istio and Linkerd implement this pattern at scale, providing traffic management, security policies, and observability across entire microservices ecosystems. Pattern 5. Serverless Architecture, the Function-as-a-Service Revolution. The challenge: managing server infrastructure, scaling, and resource allocation distracts from application development. Traditional deployments often result in over-provisioning or underutilization. The solution: serverless architecture abstracts infrastructure management completely, allowing developers to deploy individual functions that scale automatically based on demand. The diagram shows functions triggered by events, with the platform handling all scaling and resource management. Serverless provides zero infrastructure management, no servers to provision, patch, or scale. Automatic scaling: functions scale from 0 to thousands of instances based on demand. And pay per use: costs align directly with actual usage. Event-driven integration: natural fit with event-driven architectures. Considerations: serverless introduces cold start latency, vendor lock-in concerns, and limitations on execution duration and resource usage. It works best for event-driven workloads with variable demand patterns. Pattern 6, the Strangler Fig pattern, the migration strategy. The challenge: organizations need to modernize legacy systems without the risk and disruption of complete rewrites. Big bang migrations often fail due to their complexity and business disruption. The solution: the Strangler Fig pattern gradually replaces legacy system functionality by intercepting requests and routing them to new implementations. The diagram shows how new services gradually take over functionality from the legacy system until it can be completely retired. This pattern enables risk mitigation. Incremental migration reduces the risk of catastrophic failure. Continuous value delivery: new features can be delivered while migration is ongoing. And learning opportunity: teams learn about the system while modernizing it. And fallback options: legacy functionality remains available if new implementations fail. Migration strategy: successful Strangler Fig implementations require careful planning of service boundaries, data migration strategies, and routing logic. The pattern works best when legacy systems have well-defined API boundaries. Pattern 7, API Gateway Pattern, the Traffic Control Center. The challenge: client applications need to interact with multiple microservices, leading to complex client-side logic, multiple network calls, and exposure of internal service details. The solution: the API Gateway Pattern provides a single entry point that aggregates requests to multiple backend services. The diagram shows the gateway handling routing, authentication, rate limiting, and request response transformation. Gateway capabilities include request routing, protocol translation, security enforcement, authentication, authorization, and rate limiting, and response aggregation, combining data from multiple services into single responses. Gateway evolution: modern API gateways provide advanced features like traffic splitting for A/B testing, caching, analytics, and integration with service discovery systems. The pattern ecosystem: how they work together. These patterns don't exist in isolation. They form a cohesive ecosystem where each pattern addresses specific challenges while enabling others. Foundation patterns: microservices and database sharding provide the foundational decomposition strategies that enable independent scaling and development. Communication patterns: event-driven architecture and API gateway patterns handle the complex communication requirements of distributed systems. Infrastructure patterns: sidecar and serverless patterns abstract infrastructure complexity while providing consistent operational capabilities. Migration patterns: Strangler Fig provides a safe path for organizations transitioning from legacy systems to cloud-native patterns. Implementation maturity levels. Level 1, pattern adoption. Organizations begin by implementing individual patterns to solve specific problems. This often starts with API gateway for external interfaces or microservices for new applications. Level 2, pattern integration. Mature implementations combine patterns strategically. For example, using sidecar patterns to implement cross-cutting concerns in microservices architectures or leveraging event-driven patterns to coordinate database sharding operations. Level 3, platform thinking. Advanced organizations build platforms that provide pattern implementations as services. Internal developer platforms abstract pattern complexity while providing consistent implementations across teams. The operational reality: pattern tax versus pattern dividend. Each pattern introduces operational complexity, what we might call pattern tax. However, when implemented correctly, patterns provide pattern dividends that far exceed their costs. Pattern tax: additional monitoring, coordination, debugging complexity, and infrastructure requirements. Pattern dividend: improves scalability, resilience, development velocity, and ability to handle complex requirements. The key to success is implementing patterns incrementally, building operational capabilities alongside architectural evolution, and ensuring team skills match pattern complexity. Technology enablers: the platform layer. Modern cloud-native platforms provide sophisticated support for these patterns. Kubernetes provides the runtime foundation for most patterns with native support for sidecars, service discovery, and rolling deployments. Service meshes implement sidecar patterns at scale with sophisticated traffic management and security policies. Serverless platforms abstract the complexity of function-as-a-service implementations. API management platforms provide enterprise-grade gateway capabilities with analytics, developer portals, and policy management. The future evolution, pattern maturation. These patterns continue to evolve as technology and operational practices mature. AI-enhanced operations. Machine learning is being integrated into pattern implementations for intelligent scaling, routing, and failure prediction. Edge computing integration. Patterns are being adapted for edge computing scenarios where latency and connectivity constraints change implementation approaches. Security integration. Zero-trust security models are being deeply integrated into pattern implementations rather than added as afterthoughts. Strategic pattern selection, the architecture decision framework. Successful cloud-native adoption requires strategic pattern selection based on organizational readiness, team skills, operational maturity, and cultural factors that affect pattern implementation success. Technical requirements, scalability needs, performance requirements, and integration constraints that drive pattern selection. Business context, time-to-market pressures, regulatory requirements, and competitive factors that influence architecture decisions. The bottom line is that patterns as strategic assets. These 7 cloud-native patterns represent